So in this video we're doing halogenation. In halogenation you're adding a halogen across double bond. Here's your double bond, you have Br2 and CCl4 is just a solvent for now. CCl4 is not nucleophilic or basic. To be careful because if there's water underneath this arrow, there's going to be a different reaction that happens. We'll learn about that in the next video. But if it's CCl4, all you're doing is adding Br across double bond. How does it happen? I'm about to show you. And by the way, this is what we call anti-addition. So far, hydroboration oxidation was syn addition, the oxymercuration, demercuration was anti, and now this halogenation is also anti-addition. What happens, this one we didn't really do wedge or dash because there's two H's coming off right here, so this isn't even a chiral center. This one you could have made a wedge or dash, really doesn't matter. But right here, you can see if you have CCl4 and Br2, the quick way to draw the product is to erase the double bond. Right? Erase it and just put two BRs, one wedge, one dash. That's the fastest way. If you memorize this, you erase the double bond. Obviously, in the question there should be double bond there, but you erase it and you just put one BR wedge, one BR dash, anti-addition. That is halogenation. How does it happen? If you're curious, essentially what happens, this is a really small diagram, but if there's a double bond, right, your BR forms is kind of intermediate, this positively charged triangle, and then there's going to be some kind of nucleophile that goes and attacks and opens up the triangle, because assuming that this carbon's all full octets, when this hits, this bond has to break. So when the bond breaks, right, it has to break in order for the carbon to still have, not an expand octet. Now, I'm going to focus on these examples right here. Just remember that there's an intermediate in this reaction where you have a triangle. If it's Cl, there'd be a triangle Cl. Here, there's a triangle Br. So here's a positive charge Br. It's very small. But what happens is that if you look closely, now the thing is you could form this triangle wedge completely or dash completely. That's the thing about halogenation. That's why you have two possible products. You also have to keep an eye out if there's any other chiral centers, because you may have a racemic mixture, right, of what's going on with these two, because one could have been wedge, one could have been dash, but if there was a chiral center that was not changed, then you'd have diastereomers as your final product. So right here, we see that we have this going on right here. And this isn't the plane of the page, but what happens is I have my Br add across the bond, it's wedge. Okay, they form the triangle, but it's wedge. That means this methyl group naturally has to be dash. So when a Br minus comes and hits the more substitute side, okay? Rule of thumb is whenever you have a positively charged triangle, you hit the more substitute side. I didn't really go over it, but for oxymercuration, demercuration, there is a positively charged triangle, it's the Hg, and we inherently added the OH or the CH3OH, the more substitute side. This goes ahead, hits the more substitute side, that means this bond has to break. Now, what is Br? Br is wedged. So that when it breaks, this one stays wedged. But the Br that came is now dashed. That would push this methyl to become wedged. Okay. This bond breaks, the Br was both dashed, so it's still, it's wedged, so it's still wedged. The Br that came in is dashed, and this methyl now has to be pushed up to wedge. If you form your triangle both dashed, and you did a backside attack, then that would push this wedge methyl into a dashed, and this would become wedge, and this would stay dashed when we break the triangle. We're lucky because this is not a chiral center. I don't see any chiral centers. Right? What if I did this, right? Then I'd have diastereomers. Another if I had a chiral center right there. Because you're changing that. Those are non-superimposable mirror images. If you don't change that chiral center, then you have diastereomers, which is optically active. What you have right here is a racemic mixture, which is not optically active. So that's halogenation. All you're doing is adding some kind of halogen, either Br2 or Cl2 across double bond. It is, folks, anti-addition. Thank you.